In this video, we will look at the sum property of logarithms. We'll start by looking at the following example. Suppose f of x is equal to b to the x, and recall that f inverse is then defined as f inverse of y equals log base b of y. So b to the x corresponds to an inverse of log base b. So let's start by evaluating f of u plus v, where u and v are just any variables. So f of u plus v is b raised to a power of the input, and the input is u plus v. So b to the u plus v. Remember that when we have addition in an exponent, that corresponds to multiplying the two separate bases. So we can rewrite this as b to the u times b to the v. But b to the u is really equal to f of u, that's the output of f when the input is u, and b raised to a power of v is just equal to f of v. So if we do f of u plus v, that ends up giving us f of u times f of v, which tells us that when we have an exponential function, a basic exponential function like this, then addition in the input results in multiplying the corresponding outputs. When we look at function inverse, the inputs and outputs are switched relative to the original function. So by that I mean that the input of f inverse is the output of f, and the output of f inverse is the input of f. So we just switch those two inputs. So if we have multiplying the output of f results in adding the inputs, then multiplying the inputs of f inverse should correspond to adding the outputs of f inverse. So f inverse of m times n should be equal to f inverse of m plus f inverse of n. But remember that f inverse of y is just log base b of y, which tells us that log base b of m times n is just equal to log base b of m plus log base b of n. So this is kind of complicated, but just remember that log base b is the inverse to b to the x. So if we have addition in the exponent resulting in multiplying the output, then we need to switch that when looking at f inverse. So multiplying in the input of f inverse should give us addition in the output, which means that multiplying in the input of log should correspond to adding the outputs of logs. So we can generalize this to the following equation. For any m, n, and b greater than 0, where b is not equal to 1, we have log base b of m plus log base b of n is equal to log base b of m times n. Recall that when we have an equality like this, the equality goes both ways, meaning that if we see an expression like this, if we have an expression like that, we can rewrite it in this form. Or if we have an expression in the form of the right hand, we can rewrite it to look like an expression on the left-hand side. So we can start with one and rewrite it in the form that looks like the other. So let's put this to work in a couple numerical examples. Let's look at the expression log base 3 of 10 plus log base 3 of 14. If we're adding the outputs of logs, that should mean we multiply the inputs. So log base 3 of 10 plus log base 3 of 14 is equal to log base 3 of 10 times 14, which is equal to log base 3 of 140. On the other hand, if we have the expression log base 7 of 120, then we could rewrite that in a lot of different ways. So we could do log base 7 of something plus log base 7 of something else, where these two inputs just multiply to be 120. So we could have 6 and 20, because 6 times 20 gives us 120, or it could have been 10 and 12, or 1 and 120, so long as these two inputs multiply to give us 120.